Biotechnology, Inc. Our topic is micro-scale bioreactors, hurdles and solutions. My name is Donna Papacosta and I'll be your host for today. The webinar will run for about 30 to 40 minutes, including a Q&A session toward the end. This session is designed to be interactive, so please feel free to type in questions and comments throughout the presentation. You can use the questions function on the panel on the right side of your screen. If we can't answer your question during the allotted time period we have today, we will send you a direct reply after the webinar. At this time, all participants are in listen-only mode. This event will be recorded and made available for download from www.applikonbio.com. The presentation slides will advance automatically. Now we'd like to begin the formal presentation. Applikon Biotechnology is a world leader in developing and supplying advanced bioreactor systems from laboratory scale to production scale. The company supplies culture and analytical systems for early-stage initial screening through process development and up to full-scale production. Applikon is known for bringing new technologies to the market. These new technologies offer advantages in process efficiency for research and development, as well as pilot plant and production scale processes. I would now like to welcome our speaker for today's seminar, Martin Krukniet. He's a product manager responsible for small-scale culture technologies at Applikon. And now, without further ado, I'd like to hand the microphone over to Martin. Martin, you may begin when ready.
Okay, good morning, good afternoon, and maybe good evening of where you might be tuning into this webinar. I am Martin Krukniet. I am a product manager here at Applikon headquarters in Delft, the Netherlands, and my specialty is in small-scale systems and sensors. Today's seminar I will talk about micro-scale bioreactors and in specifically slightly more detail on the new micromatrix system from Applikon. And we'll be talking about the hurdles and solutions that smaller scale brings. And yeah, in general, how does Applikon or the micromatrix system handle those hurdles? So for today's talk, I'll do a short introduction on the micromatrix. We'll go slightly into the challenges of small-scale bioreactor systems and where they particularly are. And then at last we'll focus on to how we've come to some of the solutions on the micromatrix platform. Let's start with the micromatrix platform. Well, you see a picture here on the right of the platform. As a heart of the system, or say the bioreactor, we use a 24 deep well microtiter plate. That microtiter plate is and what actually is your bioreactor. We place that on a orbital shaker with a 25 millimeter diameter, so it is a shaken bioreactor system. For each and every well we have individual pH, DO and temperature control. pH control and DO control are done by gases or a single liquid by the top plate, so we actively gas all the wells from the top plate. The system can handle up to 4 control gases per individual well, so each and every well has the option of having a mix of up to 4 gases, and we can deliver a single liquid into this system as well per well. More in detail on the cassette itself. The cassette is made out of polystyrene. As said before, a 24 deep well, square well, flat bottom cassette. Working volume in this system is 1 to 5 milliliters, and at 1 to 5 milliliters is due to the shaking mixing orbit and frequency. And within the 1 to 5 milliliter working range, we guarantee a proper gas transfer and mixing properties of the system. The basis, the 24 deep well cassette, we've actually chosen that for the experience with the Applikon microflask system. The microflask system, there is a picture on the left bottom. is actually, simply said, a specialized cover for microtiter plates. With that system, we've gained loads of experience with any type of cultures, from microbial, fungal, and mammalian cell cultures. And also the designer, or the inventor of the system, Wouter Duits, has fully characterized the mixing of this system. So hence the microtiter plate platform, knowing that it can support all types of cultures, was our best choice for this particular system. Going more into detail on what the cassette actually provides, we have a flat bottom on the cassette, and that is because of the sensors that are in the bottom of the cassette. We have, from Presense, a German company, a pH and a DO optode. And if you look at the picture on the left bottom, you can actually see the two sensors, the pink dot and the whitish dot. Those are actually the pH and the DO optodes, or sensors. The pH range will go from pH 5.5 to 8.5, and the DO range will go from 0% up to 150% air saturation, which is ample enough for any cultivation you want to do. There is also a small thermal conductive pad that you can see sticking out of the bottom. That is actually a small pad that presses against the temperature sensor, which we need for the temperature measurement and subsequently the control of a particular well. And the temperature range we can handle is 15 degrees Celsius up to 45 degrees Celsius. And this is process temperature. Going further, a schematic of one single well. The DO, or the oxygen concentration, and pH are regulated mainly by gases, while all gases are entering the well via a filter, a 0.22 micron sterile filter, and also the gas out is also filtered. Next we see in the top plate actually the liquid delivery microvalve, which is a small microvalve able to dose from 50 nanoliters boluses and bigger, and we'll come into more detail later on. Going to the bottom of the cassette and in contact with the media, of course, we have the pH optode and the DO optode, or pH sensors and DO sensors. Going lower, in orange we actually have a small heating and cooling element, Peltier element, so each and every well has its individual temperature control that can also, to a certain limit, slightly cool. To have proper temperature control, we have a well temperature sensor that senses the temperature of the well itself. And for added accuracy, we have a second temperature sensor that actually measures the heating and cooling temperature of the heating cooling pad. In that way, we have a algorithm that can actually compensate for the influence that particular heating and cooling pad has on the well temperature sensor. So with those two sensors, we can actually have more accurate temperature measurement of a particular well. So going to the complete machine, so we have the whole main console that you see here. What you do not see is actually the computer or laptop that needs to be connected to the system. It is only there for the user interface, or the human-machine interface. As soon as you have your complete recipe, you send the recipe to the micromatrix, and it will actually fully on its own continue the recipe regardless of the connection with the computer. But back to the location of the parts, the chamber itself is actually thermostated, so we have a temperature control for the particular room, and this is only to help the actual process temperature of the cassette. Second is the orbiter. It's actually, you cannot see it, but we've built it in the system. and it holds the black box you see here. The black box is actually the cassette holder, and it is also the pH and DO measurement system, including the temperature system. So all temperature measurements and pH measurements are done in there, and also the temperature control houses in this black box. For the gas delivery, in the top of each and every well, we have a gas delivery module which is built in. As I've said before, we have 4 gases per well, so a total of 4 times 24 small gas valves that can help control anything you want in the cassette. We have liquid addition bottles. Although we have a single liquid feed for each and every well, so there's only one liquid valve for one well, the 6 valves are connected together with one liquid manifold. So one row of 6 wells is actually connected with one single liquid. So it would be possible to have 4 different liquid feeds in 4 individual rows. So row A, B, C, and D could have a different liquid feed. Hence, we've shown here 2 liquid bottles, which is possible to do. Last, we actually have a barcode scanner. We found out with previous systems to get the calibration values of the cassette into the system can be quite elaborate. So what we have done, we've integrated a QR or 2D barcode on the cassette. You can actually scan that barcode prior to putting the cassette on the machine, and that barcode actually has all the calibration data of the pH and DO sensors of the cassette. So there's no need to manually put all the data in. You can just scan the cassette and it directly is ready to go. Now going towards some of the challenges you have with small scale. Well, one of them logically is scale, is size. Everything is smaller, and some of the problems that poses are in these areas. So one of them is mixing. We can, of course, try to manufacture a very small impeller, similar to a bigger bioreactor, but it does mean on this small scale the hydrodynamics change as well. And if you look at an impeller-based mixing system, especially this small, the mixing properties will actually be different from the shear forming properties, so the shear on your culture. And to have 24 individual small mixes is technically very challenging. So hence we went to what we know, the orbited system of the microflask. So hence, in a fairly simple way and a very robust way, we have similar mixing as in bigger systems. One other thing, the gas delivery has to scale. Luckily, gas is easy to manipulate, so it is possible to scale the gas delivery fully down to smaller systems. So that, luckily for us, is no challenge. And then the last one, liquid delivery. That can be a challenge. It is, if you look at a normal peristaltic pump in a bigger bioreactor, normally you just keep on pumping until you have a droplet forming that actually drops into your bioreactor. If the volume is big enough, then that small droplet doesn't matter in the whole volume. But the droplet size doesn't change. But our working volume does change. So it is imperative that we have a different liquid delivery system that can deliver much smaller much smaller boluses than a large droplet. And last, the speed of the culture. Not that the culture itself is smaller or faster in a bigger system or in a smaller system, but you have to measure those changes in a very thorough manner. And because we have a very small system, we cannot use classical sensors. So we cannot use a classical pH or classical DO sensor because those would just not fit. So hence we have to choose a proper measuring system so we can actually measure those changing conditions and directly act on those to prevent your culture from going into a mode where they don't like growing. Okay, so I slightly elaborated on the mixing as well, of course. We've based it on the research done by Wouter Boets, the inventor of the microflask system. He fully characterized or looked into the mixing of microtiter plates. Hence he simply put a webcam on an orbital shaker, and some of those pictures you can see on the right. What he found compared to round wells, square wells, small microtiter plates, the square wells really act as baffles in a fermenter. And as they work as baffles, they greatly increase the gas-liquid interface, or otherwise said, the gas transfer into your media. So that's a really good thing to help, and it also induces shear, not that much that it can actually hinder your culture, but enough that it can mimic a impeller-based bioreactor system. The gas transfer is comparable with a 3-liter fermenter. So, and this is for the microflask system, which has a passive aeration system, so it's just diffusion. And mixing times are smaller than 1 second with the 5 milliliter volume at 300 RPM. So it is a very good system for mixing to have square wells with this microtiter plate. If we now go to the gassing, we have 2 options generally to provide gases into a media. One of them is simply sparging into the headspace. Now, I'm not sure if sparging is the correct word, but getting gas into the headspace. A big advantage there is compared to sparging, you're not bubbling into the media, so you do not need any antifoam, or not more antifoam that you're used to in your normal pre-micromatrix systems. Compared to sparging, we have found that okay, you're bubbling into the media, so you have bubbles that also exchange gas into the media for as long as they're in the liquid, but actually that residence time, or the residence time of those bubbles, is very limited in these very small liquids. A bubble has a certain speed. You can imagine if you have a column of 20 meters of media, that bubble will take a very long time to reach the top. But in this case, we have a very small well with only maximally a 3 centimeter, maybe translated into inches, a 1 inch, a 1 inch liquid volume, so the bubble retention time in those small liquids is very limited. And our experience with previous systems has shown that there's barely any influence or any advantage above sparging, bubbling into the media, as compared to have a well-shaken system where through baffles you can actually have that gas-liquid interface be much more turbulent and actually get an equal gas transfer rate bubbling versus just headspace aeration. The small-scale liquids, we have in any system basically, we have 3 options to get liquid into our systems. Well, one of them is of course manual. There are some disadvantages. Well, manually, one thing is you normally get the cassette or the bioreactor off of the shaking platform, in the case of shake flasks or microtiter plates, and then you take it to your laminar flow cabinet and actually work with the cassette there. So the disadvantage is you actually stop mixing and gas transfer as you take it off your control platform. One other thing, you have to open those cassettes. Those wells, you're actually posing a contamination risk. The advantage, of course, is you can do anything with it. You can sample, you can pipette any liquid, big volumes, large volumes, so that's fine. Next in line, a pipette robot. It also has a similar contamination risk, of course, because you're opening your well. It could be that if the system is working, and that's actually point 2, if it is activated for a feed control, it cannot do anything for pH control. So a pipette robot can only do one task at a time. And that can also mean it is fairly slow. So it can easily take up to 2.5 to 3 minutes per well for a pipette robot to get a liquid in or out of a well. So if it has to address 24 wells in one go, it can take up to an hour before it's done with one task and then continue with the next one. Of course, the big advantage is pipette robot will never complain. It won't complain in the weekend, it won't complain when it's late in the evening or when there's a World Cup football tournament going on. So that's the big advantage of a pipette robot. But knowing those things, we've actually chosen a small micro valve. Main thing is it is there when you need it, so it is always on top of your liquid. It is an instant feed or an instant delivery, so there's no wait because it's already there. You do not need to open your well to get liquid in. The control will continue because we're just mixing continuously. pH control is still busy, DO control is still busy. We can add liquid simultaneously. Disadvantage, of course, is it is only a single liquid versus all the other ones on top. Going more into the speed of a culture. So one of the things that changes most rapidly is, of course, the dissolved oxygen. So it's essential that your oxygen transfer must be on par with the oxygen uptake rate. So if we now simply look at a Pichia culture, which is a general, say, middle-of-the-road oxygen consumer that has a rough 50 millimolar of oxygen per liter per hour consumption rate. If we now take the oxygen saturation of a physiologically salted media, that is 0.2495 millimolars per liter of oxygen. If we keep that in mind and assume that this culture, the Pichia culture, has a constant oxygen uptake from saturation down to 0, so that is of course not what will happen in real life, but this is an idealized case. And as I said earlier, the Pichia is it's not top of the line in oxygen consumption. There are E. coli cultures that can out-consume Pichia easily. But if we take this in account, and if we simply take the saturation of a culture and divide that by the consumption of a Pichia culture, you can actually go from a saturated oxygen or air-saturated media down to 0% in 18 seconds. So knowing these sort of numbers, it's essential that you have a system that can measure these sort of small changes quick enough. Otherwise you might deprive your culture of oxygen or maybe pH steps that go upward. So speed is essential, so hence in the micromatrix system we measure the DO and the pH every 10 seconds. We did take the control cycle time of both loops up to 20 seconds. For pH doesn't change that quick, so that's no problem there. But for the DO, we were actually trying to do it too quick. So with a shorter cycle time, we would actually get a very unstable DO. So with 20-second cycle time, that went along better. And of course, what we can do in our system is a simultaneous pH, DO, and liquid feed all at the same time, depending on how you have programmed the system to act on pH, DO, or liquid feed. There's no need in pausing any of the parameters or any of the deliveries that you need. Going more into the hardware and then more into the microvalve. On the left you see a complete setup of the microtide cassette. On the bottom, the dark gray. And then on top of that, in beige, we have the top plate, which on the middle picture is actually the bottom view of a top plate. And in the top plate, you can see the microvalves, and next to the microvalves are actually the holes that are needed for the gas in and the gas out. And in this picture, there's no gas filter bar, so you do not see the filters. Those are added at a later point. But you do see a small close-up of the microvalve. The microvalve itself is simple enough. It is a solenoid-style microvalve, meaning it is simply just a coil that gets energized and it actually pulls a plunger open. The microvalve is fed with a pressurized medium, so we have a small metal media container that we pressurize up to 1 bar. That 1 bar is offered to the microvalve, and as soon as the microvalve is energized, it opens shortly and the liquid is literally shot out. And due to this action, it is actually possible to dose very small volumes, and it is also not sensitive for viscous media, so up to 60% glucose is actually not a problem with this valve. And of course we have a single microvalve per well, where we can only handle 1 liquid at a time, and we have, of course, of that very quick measurement and also the control action, we have an instant addition, we have no lag. So looking even more close, the valve itself is a 5 millimeter diameter. You're actually looking at a sapphire window with a small hole in there, and on the other side of the sapphire window you can actually see a small red ruby. So it is a hard-on-hard seal that is happening there. The additions it can handle start from 50 nanoliters with an accuracy of plus or minus 5%. If we go to 500 nanoliters, we get more accurate and we're down to plus or minus 1%. The valve itself can handle feed solutions, base solutions, low concentration acids, glucose solutions, anything you can think about. And unique to the micromatrix, you can actually program the valve for just simply a constant flow, so giving boluses over time. Set point control, so you can implement the microvalve in a pH loop, and it would even possible to integrate it in a DO loop. You could also, on the micromatrix platform, use a cascade for using air initially for DO control, and maybe as a second step use the microvalve. And last, what the micromatrix is capable of is actually a time and event-based control. And with the time and event-based control is actually a specific measurement. If that is above a certain threshold value during a time of a certain period, then we can program a action to be done, be it a pH step, be it a bolus feed of a liquid or anything else. On the right side, this picture you see there is actually a high-speed camera recording of the microvalve shooting out small liquid droplets. Just as an example, a 50 nanoliter droplet is so small on a surface of liquid you cannot see that droplet touch the water. There are no ripples, no nothing. So these are very small volumes we're talking about. Then, as an example on how that can look, this is a Pichia pastoris culture. In blue you can see the dissolved oxygen profile. In red is actually the accumulated liquid dosage. What you see here is a grown Pichia culture, so it has its biomass, and we're actually inducing the Pichia postoris with methanol. The trigger or the time and event-based action we have programmed here is that the DO needs to be equal or higher than 80% air saturation for longer than 60 seconds. Then the system will actually give a bolus of 100 microliters of methanol, and it'll actually give that bolus in small dosages of 50 nanoliters. So the system itself programs or knows how much additions it needs to do, how much of those small pulses it needs before it reaches 100 microliters. As soon as it's done that trigger, it'll wait until the next event when the trigger again happens. So what you can see here in this graph, the initial drop in DO is with the very first methanol feed. Then as a second spike, that is actually where the Pichia has ran or has consumed all the methanol. So at that point the DO spikes, and this is where the speed comes into. The DO spikes are within 60 seconds, so it's a very quick spike, and as soon as the spike has been seen for more than 60 seconds, the second bolus is done. Hence the DO drops down instantly, and you can see this has been running. This is a single well for 100 hours without any problem. Of course, this is one single well. This can be done in each and every well individually. So with all individual triggers, you could even program them all differently, but in general it's just one type of trigger. And one other thing that is possible with the micromatrix is to program a global trigger, where you can say, okay, if 50% of my 24 wells is actually complying to my parameters of the trigger, then just dose every single well with that particular trigger. And again, speed is of the essence here. If you cannot dose this quick enough, you can have cultures that are being starved of their feed, which can have a dramatic influence on your culture itself. Well, with that, I want to conclude this webinar. So I want to thank you for your attention, and if you want to learn more about the system, please go to www.micromatrix.com, and if you have any questions, please post them there and we can have an active discussion on the system itself.
Yes, thank you very much, Martin. As Martin said, we're now moving into the question and answer part of our program, and at this point I'd like to invite our audience to continue sending questions or comments by using the panel on the right-hand side of your screen. And we do have some questions for you. The first one is it possible to measure optical density in each well?
No, with this system it is not possible to do an online optical density measurement.
Is the microvalve capable of delivering viscous liquids such as concentrated glucose or glycerol?
There is a limit to the viscosity the valve can handle, but we have successfully tested up to 60% glucose without any problems in the small liquid deliveries.
And here's another question. How is the dissolved oxygen sensor and temperature sensor calibrated?
The DO sensor is actually calibrated at the pre-sense factory, so it comes pre-calibrated. It is of course possible to recalibrate it yourself on the machine with just air. And the temperature is also a factory calibration. The temperature sensors are actually on the machine itself. So at Applikon we can calibrate those sensors in a proper manner so the temperature is done correctly. And as the sensors stay with the machine, they are just normal electrical components. They are barely service-free. No, they are service-free, sorry.
Okay. Do you have any data to show from various cell lines in terms of growth?
We are working on those numbers, yeah. So the system is fairly new. We're gathering more and more info each day. At the moment, mostly what we have is on Pichia, and we have a few E. coli runs, and up to now that is what we have.
Another question, can one choose or program for between sparge and overlay or both?
The micromatrix is only designed to do overlay, so there's no way of sparging, bubbling into the media.
And how would you take a sample from a well?
At the moment, sampling would be done manually, with the disadvantage of taking the whole cassette off the machine towards your sterile working area and then manually taking a sample. We are working on an online sampling system, so the system can run continuously, but that is still being designed as we speak.
Mm-hmm. What about the signal-to-noise ratio of the DO and pH sensors?
The DO and the pH sensors, for the DO, the signal-to-noise ratio is pretty good, as the optics are very close to the sensor. So there isn't barely any loss in between the signal from optics to the sensor. The sensor itself is more sensitive at low DO than at high DO. So at air saturation, we're looking at an absolute accuracy of plus or minus 3%. And at the low DO, we're looking at an accuracy of plus or minus 0.1%. Mm-hmm. For the pH, that's slightly different, of course. There at a pH 7, we're looking at an accuracy of plus or minus 0.05.
Is it possible to switch to the liquid being delivered through the microvalve during a run?
Yes, at any point in the run, you can actually change your whole recipe, your whole set points or control algorithms, and actually send that to the micromatrix, and it will continue with your new settings. So on the fly, changing your parameters is no problem at all.
Mm-hmm. And what is the maximum liquid flow rate for the microvalve?
Well, in the micromatrix, in general, we limit the flow rate because we only have 5 milliliters to work with, so it's fairly easy to actually fill up the well to a level that's too full. We also use this particular valve in our mini biot systems. Those are 250 or 500 ml vessels. If you fully open this micro valve, you can have up to 8 milliliters per minute without any problem.
And what is the accuracy and precision of the pH and DO sensors?
Well, I've just mentioned it actually. The accuracy for the DO is plus or minus 3% at air saturation and a high DO, and for low DO it is at 0% or 0 to 10%. It is plus or minus 0.1% DO saturation accurate. For the pH, at a pH 7, the accuracy will actually be plus or minus 0.05.
Thank you very much. That is all the time we have for today. If your question was not answered, we will email you a direct reply. I would like to thank everyone for attending today's webinar. Don't worry if you missed part of the presentation. Simply visit www.appliconbio.com, where our webinars will be archived. If you want to share this presentation with your colleagues, simply email us their name and email address, and we will send them a link to the archived presentation. Please join me in thanking our speaker for today, Martin Krukny. And thank you all for your time. We hope you found this webinar informative. Have a great day.